So I want to report on work by, which is very recent, with Reza Ghessairi. Who's at Berkeley. And Okosh Jagannath. Who's at Waterloo. And so this is very recent work, so recent that it's not yet published, not yet even an archive. So this is also why I want to give the first talks about it like this, so that I see how to present this. But it will be submitted and posted very quickly. So the question we are looking at here is a question about, we asked ourselves, what do we really know about stochastic gradient descent in high dimension? Right? Stochastic gradient descent is the way every optimization is done essentially in, in machine learning in real life. We've studied for some model things, we've studied all sorts of other algorithms, and I'll discuss a few. Of course, you could think, if you're a physicist, you would think Langevin, you would think gradient descent, you would think many other things. But in the end, it's really stochastic gradient descent. So we wanted to understand stochastic gradient descent. What would be the advantage of it, or what does it do? Better than gradient descent, for instance. And, but in very high dimension. Right? So there are works on that. Some serious work, but we wanted, to start from scratch and see what we can understand. So, so let me just start with the simplest settings of all that. So we will have data. My data will be called Y. So IID. So, oh, by the way, of course, so I guess you all know what stochastic gradient descent is, otherwise I will describe it a little more in detail. So let's say in some space RD, and then we will have, with the distribution, let's say P, and so that's the first bit. Then you have a loss function. So here, this means you have already chosen your statistical method, maximum likelihood, or if you're doing machine learning, the architecture of your network, all that is done. So this fixes this loss function, and the loss function will be a function I call L, which goes from R, or let's say a subset maybe, to R, where this X is a subset of, think the whole set, that makes not much difference, of R to the P. So this is the space of parameters. This Y is, let's say this is with values in a set Y, if we want. It doesn't have to be the whole of RD, of course. And so this, of course, is our loss function. And we want to do, and with that, of course, we immediately can write what SGD is, stochastic gradient descent. So of course, as you know, stochastic gradient descent has many variants. I cannot study all of them. Some of them are probably. So if you really do stochastic gradient descent in a practical way, you will probably do something more complicated than what I'm describing here. So this here, we call it online or one pass, right, if you know what that is. So the online version is, so we have to give you a number, which will be the step size or the learning rate that we'll call delta. And of course, stochastic gradient descent is the simplest of all algorithms to try to find. So here we'll try to find minima. So in discrete time, it will be xt is xt minus 1 minus delta grad L of xt minus 1 and of yt. delta. It's a number, a positive number. You will see, it plays a big, big role. I'm sorry?
You don't specify for a moment.
No, no, not at all. So this is one pass, and online if you want, which means I take one data point. But of course, I have to give some initialization. I will start with the distribution mu on whatever I called it. The space of x's was on x, right? So you start from somewhere, and then you run this thing. This is the simplest thing you can do, right? So it's one pass or online, just because I take these guys and use them one after the others, one after the other. Of course, if I have a limited amount of data, which of course is what happens in real life, this constrains the number of steps I can do if I do that, okay? Of course, I imagine everybody knows that, but just in case. You could do other things. You could, for instance, do small batches, right? Instead of taking just this term, you could take a little sum on maybe k of them, right? That would be a mini batch of size k, right? So here, I'm taking the mini batch of size 1. That's the extreme case. You could take the mini batch to be the full thing, right? And that would be simply gradient descent for the empirical loss. Okay, are you all with me here? I don't know you, so maybe I'm just saying trivial things, but.
What is the stochasticity?
What?
What is the stochasticity?
It's just in front of you, this guy. These are IAD. So every step, you choose a y, and it gives you a random direction, okay, for your gradient. And there are in fact, so that's a good question. There are two sources of stochasticity, each step, and of course the starting point, which you pick randomly. All right. Of course, you could also do more complicated thing than doing mini batches. People do reuse, right? So you go with one batch, whatever the size, you do one pass, whatever the size of the batches you do, and then maybe you do a random permutation of all those numbers and do it again, right? So practically, there is much more to study than this. This is the simplest thing, but on purpose, it's at the other extreme from the gradient flow for the empirical loss. All right, the gradient flow for the empirical loss would be to replace this term by the average of all those terms. Okay, good. So we want to understand this. So this is a very, very classical thing to do. And it's understood in this context. You know, D is fixed, P is fixed. Okay, so let me say what you all know. This is, first, it's not new. Of course, it has been introduced by Robinson and Monroe decades ago. And of course, the result everybody has in mind is that this converges, right? When the step size is small enough, fixed dimension. And when you have enough smoothness properties for everything, this converges to the flow of the population loss, the gradient flow of the population loss, which would be, so let me introduce those notations. Maybe I would put them here. Yeah, I will call phi of x the population loss, which is the expectation of L of x, y. Expectation here is, of course, for y, under y. Right, so that's the population loss. Of course, this population loss you don't really know. You don't have really access to it, but you have data. And in normal situation, in situation where all the dimensions are finite and you have a small enough learning rate, this will converge to the gradient flow of that. Right? So dxt, you expect the gradient flow of that would be that you expect something like this. In the limit, of course. Right? This should be close to that. You take this guy, which is here defined at discrete time, you interpolate linearly, this thing will converge to the solution to that. All right? So no surprise. Now I'm interested in large dimension. Okay, so I want everything to be large. So this dimension will be large. So I will introduce an extra parameter n, and I will say everything depends on this n, and everything is large. So this p depends on n, L depends on n, and so this learning rate depends on n, and here I could put many n's here, right? And I'm interested at what's going on. Of course, this m may depend on n, and what's going on in the situation where the dimension grows. So there is one first remark, and I'm not saying here in what regime. I'm not saying linear regime, that one dimension is a multiple of the other or whatever. For the moment, I'm just asking a question like a mathematician. What can we say, right? So, and in particular, is this kind of thing still valid? Right? Does this converge in certain regimes, at least, to the flow of the population loss? Is it still true? So this, of course, is this dynamics is in dimension p, right? X is the parameter, the dynamics in the space of parameters in dimension p, and this p is supposed to be very large, tending to infinity, right? So now I want everybody to tend to infinity. So the convergence of this to that means nothing, right? You can't even state it, right? So how would you do that? But this thing is supposed to be in infinite dimension, right? If your p is going to infinity. So a natural thing to do, of course, you could try to define infinite dimensional objects. As mathematicians, we love them, right? But let's not do that. Because in practice, you probably don't want to know everything about x, the whole parameter. If you think at everything you've done in statistics, you always are interested in a few functions of x, of the parameters, right? So what you're really interested in are what we are calling summary statistics. So it would be something like a function u from our space of parameters, which was R, let's say, R Pn, to some fixed Rk, right? So k now will be fixed, say 5. And now you're looking at the 5-dimensional projection, if you want, of your stochastic gradient descent flow, and you want to see if you can say something about it, right? So this u would be a u sub n with my convention. Of course, there is no reason to, so okay, maybe I should say one more word. When we are in finite dimension, this is, of course, this corresponds, this is a very simple object. The fact that this converges to that is essentially a law of large numbers. You, of course, can go further, try to introduce a diffusion term. That would be a central limit theorem. And that works. Usually, in good cases, it works. And you can also do large deviation if you want. Because here, at the basis of this, you have an infinite sequence of, or a large sequence of IID random variables. So, of course, you can do everything is a consequence of elementary things, right? Law of large numbers, CLT, large deviation. All right, so here we are hoping to have a limit theorem, not for the whole object, but maybe for a projection of it, which would be interesting. Okay? So when can we imagine that there might be a finite dimensional object that is interesting, right, in this infinite dimensional object? Typically, for instance, if your population loss, imagine that this, in fact, so this is a function of something which is a diverging dimension, but imagine that this is, in fact, a function of a small dimensional thing. Very many models are like that, right? So, and then it would be natural to follow that statistics, right? So imagine that this is a function of some, let's say, psi, of some m of x, where m is now a function from r to the p to some r to the whatever, L, finite, right? Then it's natural to imagine that these are really the statistics you want to follow. And you will see in practice, this is very often the case. But it could also be you do classification in a situation where you don't have any idea that the signal, if you want, is finite dimensional. There are plenty of very interesting results recently showing that, at least at the end of your, numerically, of course, nothing mathematical, For instance, I'm here thinking of the fantastic work by Papian, Han, and Dono a few years ago, where you see that so for hard classification tasks in large dimension, where you don't assume a priori that the signal is finite dimensional like this, you see a finite dimensional, very structured thing emerge at the end of your trajectory of the SGD, right? So this is what they call neural collapse. So it's not an unreasonable idea to think that maybe there are good finite dimensional projections that you can follow and do something with, okay? But of course, if you take a projection like this, there's no reason that it would satisfy the nice equation, right? So you need some assumption. So it will be a summary statistics. So imagine that this theorem is true in finite dimension. If you take u of xt, what will you get? You know, du of xt will be negative grad phi of xi, and then grad u of x. So you want this to converge to something which is a function of u, right? So that's the first assumption. So we will say that something is summary statistics if the following thing, you need first the grad phi of x, grad u of x, to minus some function f, little f, of u of x to go to 0, right? And then you need two more. So this one does not depend on the step size for the moment. And then you need that delta L u of n of x minus another function g of un of x goes to 0. We'll tell you what this L is.
Sorry, here the average is over what?
No, it's not an average. It's just the inner product.
Okay, yeah.
No, it's not an average. I never note averages like that. That's a physicist thing. So, and third, okay, if you don't like this, put a big dot here. Yeah. It's the inner product. Yeah. And 3, you would have delta n, the step size, times j, v, jn transpose of x, minus some matrix sigma of un of x, go to 0. So here I have to tell you what j and l and v are. So, here. So let me put them there. So, phi is the population loss. H will be the random part, if you want. So that's the loss. I should put a y here, of course. The loss minus the average. And V will be the covariance matrix of H. Okay? So expectation of the covariance matrix of gradient of H. And finally, L is a second order differential operator, which is just 1/2 of sum of Vij di dj. Okay, so if I give you the loss, population loss, you can compute H, you can compute V, this covariance matrix, you can compute this operator L. This is the operator L here. I didn't tell you what J was. J is just the Jacobian. J is for Jacobian of U. All right. So if you have these 3 conditions, 1, 2, 3, we say that UN is a good summary statistics. All right? And of course, this is just built on purpose so that once you have that, so the theorem would be if something plus plus the fact that UN is a good summary statistics, then your U converges to, so this projection converges to a U, which will be simply this. So not an enormous surprise. I'm telling you, if you have this, of course, this has to be made a little more quantitative, but that's the idea. Then you have a convergence to that, okay? So your projection converges to something, which is just a solution of an SD. This looks like very, so I didn't tell you what the ... right? But I'll come back to that. So this looks like something very natural, unusual, right? What would be the finite dimensional situation? Right? In finite dimension, if you just take u of x to be x, you don't even have to project because you already are in finite dimension, right? But you could project. Then, if you accept that x goes to the flow of the gradient, I mean the gradient flow of the population loss, then this term should be it. So in finite dimension, you should get f, g should be 0, and sigma should be 0. Right? So the convergence to the gradient flow of the population loss should tell you something like that, but with g equals 0 and sigma equals 0. All right? So here I'm saying there may be other terms. So this f term will be called so these guys we call the effective dynamics. Okay? And so how do we call this thing? I forgot. Yeah, F is called we call it the population drift of U. G, we call it the population corrector. I've seen you. And sigma, the diffusion matrix of U. All right? So for the moment, of course, it's important that I fill in this dot, but the result is this, right? Yes. I'm sorry? I'm sorry? This is convergence in distribution, right? This, you have your UN, which is something in RK, right? I'm sorry? It is. It is. UN lives in RK, K is fixed. The dimension of what?
The domain of definition of UN.
Uh-huh. You don't care. UN lives in RK. It's a random object. It's a random trajectory in RK. Because it's UN of x. X is in R, whatever I said, P. UN of x lives in RK. Let's say it's a two-dimensional projection. It lives in a plane, right? What?
Is Pn varying with n?
Yes.
So the input dimension is varying with n?
No. K is fixed.
The output dimension?
There's no output here. It's a projection. So this guy is fixed. Right? So.
Can you give some insight on the G? Because G is some kind of bias that you get from projecting from high dimension.
No, it's just the Jacobian. UN is a map from here to there.
Not J, G.
Ah, G. I will do only that. Wait. I give you an example. Of course. So here's a very natural. No. Even sigma is not what you think. So G. Why would you have a G? That's what I'm telling you. If you believe this, you don't have an F, you don't have a G, and you don't have a sigma. Right? So in fact, there are cases where you do have them and cases where you don't. I will try to explain.
I have one question which I think is related, which already occurs in the standard way you presented the stochastic gradient. You are interested in trajectory convergence, so convergence
Of the path, yes.
to the trajectory
Yeah.
given by the differential equation. But to do this for stochastic gradient, you would need rate delta.
Yeah, I agree. You need a regime of delta that is good enough. I agree.
That decreases with t.
Yeah. Of course, that decreases with that. Absolutely. Absolutely. We'll see that. Okay? So now I need to fill in the ... So, and I in fact need to explain what these things really mean. So for that, of course, it's technical for just for 1 second, because if you look at the if you look at the literature on these things, all the assumptions about, so this is where I want to be very careful. That is, you have many results with Lipschitz assumption on all sorts of things, but then you have to very carefully follow the role of the Lipschitz constant in this whole thing. And typically when the dimension diverges, this creates disaster. So we wanted to be very precise. We are, in fact. So let me give you the, where did I put this? Just a second. Yeah, it's here. So first we assume, even to make this, these assumptions here. Okay. So we first assume that, so that our UN are, let's say, C1. That's the minimum we can assume. We assume that there exists a sequence EK, an increasing sequence of compacts that fill the full space, the full RK. So because here I'm on an unbounded thing, so I will come back to compact things. The thing I'm saying here, this convergence to 0, should be uniformly, this is a function of x, they should be uniformly, so the assumptions we want is 1, 2, 3 should be uniform on u minus 1 of ek. So that means the soup over x in that. And then the dot, dot, dot over there is, we call that, we say that the pair, ln, so we say that our system is, let's say, delta n localizable. So that's where the step size plays a role. If we have the following. So first, the first few derivatives of u in operator norm are bounded by a constant, which would delta n, and there you have to follow this properly. This uniformly. Then you have the gradient of the population loss should be bounded. Same thing uniformly on each of these ek. And the expectation of the cube of h should be bounded again by another constant, delta n to the negative 3/2. And then you have a final thing, which is that the expectation of the covariance matrix to the power 4 should be bounded by delta n to the minus 2. So you know, this answers your question. Right? This tells you something about the choice of the delta n very precisely. These assumptions are less strong than saying the usual thing like it's globally Lipschitz or whatever. We're saying locally we have this type of thing. The important thing, of course, is the scaling that you get here in the step size and here and here. So let's discuss, I mean, this is too technical to swallow, but of course, it's just the assumptions you need for the convergence theorem to be true. Now, let's discuss something very clear here. If you have a system which is delta n localizable, just look at this, and you will see that if you take now a delta n prime, which is smaller, which is little o of delta n, so it's much smaller step size, it will still be localizable. Right? So, in fact, you will have a full regime of delta n's, which will be localizable, for which the theorem will work. And then you would have an upper limit to this regime. This is what we will call the critical regime. The lesson, if you just want to remember that, is that as long as you are in this subcritical regime, which is wide, typically the limit you obtain is the same as infinite dimension. And then you have this critical regime where many more interesting things happen, which are very useful. So typically, but now, so if this is easy to see. If you take a smaller delta n, these terms will be larger, so the assumption will be true. Now, something else. If you look at these guys, if you have this limit, and now take a smaller delta n, then if this one converges to G, if you take a smaller delta n, it will converge to 0. Right? And same thing here. But not here. There's no delta n here. So if you have a theorem like this for a scale delta n, which is delta n localizable, if you take a smaller step size, you will still have the theorem, right? But you would have lost G and sigma. All right, they will be 0. If you take a smaller step size, you will get the usual thing you get in finite dimension, right? Because the first term, the population drift, is the same as the one you would get in finite dimension. But then you have these critical regimes where new things can happen. You can have a ballistic correction, and you can have a diffusive correction. Now, in all the examples that I could show, you would have, it happens very often that, of course, G and sigma are 0. It happens very often that it happens also that G is non-zero and sigma is 0. Every time there is a sigma, it is a very degenerate diffusion. It's no longer elliptic, right? Like you get in finite dimensions typically, right? So the sigma are typically, in all the examples we have, are typically extremely degenerate diffusion, right? Good. So that's the abstract nonsense. So now, of course, I won't. So let me explain maybe one more thing. The way I explained it like this was, you have your UN in length scale 1, and then you have a time scale which is essentially given by delta n, and then you have a limit theorem. Now you may do with the same theorem, you may ask yourself, okay, you have a dynamical system. Okay, that's a dynamical system. Let's imagine for simplicity that you don't have a sigma. Right, so now you have a dynamical system in your RK. Once you have found, of course, the art of finding a sufficient summary statistics is difficult, right? And you could find many different ones, right? So, but once you found a summary statistics, you end up with this dynamical system here. Now the problem is a problem of dynamical system in finite dimension. So, of course, what you want to understand are the stable points or the components of the stable points of this dynamical system, right? Because then, of course, your system will typically go to these things. Are they related to what you want to find when you do machine learning or statistics? For instance, are they stable fixed points or unstable? How would you transit from them? So, for instance, one thing you may want to do is take one of those one of the fixed points or the connected components of the fixed points, starts there, and then zoom in, right? By looking at a different scale, the right scale. If you do that, you again have typically a summary statistics, and you can again apply the theorem. So typically you could start with something which is ballistic, then it goes to some stable manifold, you zoom there, and then you add a diffusion term, right? You have a whole family of things like this. It's not just one. And I will show you a few examples of that, yeah?
So why for diffusive if it's the scale linearly with time?
I'm sorry?
So it's not a Brownian motion here. It's
Oh, I'm sorry. I say diffusion term and there is no diffusion. Thank you for that crazy result. Of course this is Brownian motion in RK. Thank you very much. Otherwise it makes no sense what I'm saying. Okay, thank you. All right, so let me give you examples, right? So let's start with the workhorse I prefer for understanding complicated stories because it's rank 1. So, and then I will go. So I will give you an example with spiked tensors, spiked matrices, or things of that nature, which is a statistics problem, which can be hard and which is very well understood now. And then I will give you an example with classification with 2 layers, Xor, this type of thing. But I don't want to go directly to the Xor model, the very simple 2-layer thing, because there you will see that you have 625 fixed points for this. So a little painful to write. So let me start with simple things. So the first simple example would be matrix or tensor Pca. Right, PCA for principal component analysis. So that's a very elementary statistics problem. And you will see that the dynamical system is not very complicated. So of course, the data you have here is you have, and here I'm putting this in rank 1. You could do it in rank 17, it would become a little more sexy. But here it's a simple thing. You have a unit vector in Rn. Let's say it's unit and unknown, right? That's the one you want to estimate. And what you have access to is this. It's just a noisy version of this, right? So you have this fixed vector. So this is a tensor of rank k. If k is 2, if k is 1, it's a vector. If k is 2, it's a matrix. If k is 3, it's a tensor. So you have a fixed tensor, which you do not know. And you add here a random tensor. That's the random noise. Each component of your tensor has a little bit of noise. So you assume that the WIs are IID, Gaussian. So I could put a variance here to have a small variance, a small noise, but instead of putting a number here, I put it there, so that the lambda now becomes the signal to noise ratio. Okay? So depending on so when lambda is large, you have a lot of signal, it should be easier to find a thing. When lambda is small, when lambda is 0, you cannot find anything. So the results about that are very well known. I imagine you've already heard this, but let me say that quickly. What do you think, Julio? Should I just go fast? What?
If you say something quickly, I think it's
Yeah. So what you want, of course, is there are different problems you may want. The one I will attack is at the end of this list of problems. The first one would be to detect V. Right? You see this sequence of tensors. Is there a signal? Then, so for that you have, so there is a special IT threshold, information theory threshold, such that when your lambda is below, it scales with everything. I don't want to give you the numbers, but okay. So when you are below that, you can't even detect. So that's the information theory bound. So what does that mean? You can't detect. If you look at the distribution of the system with the signal and the distribution of the system without the signal, in total variation, the distance goes to 0. Total variation means you cannot find one event or one observable that will distinguish them. So just forget it. Okay, you can't. Now, if you're above that, a priori, this tells you, in fact, you can detect. And so, in fact, you can find an observable that will make a difference. So typically, it means you can find a statistical procedure that will make a difference. It happens here, then you can even estimate. So now you take, so if for instance, you are a poor statistician, you know only one method, the first you learn, which is maximum likelihood. You apply maximum likelihood, the threshold for maximum likelihood should be above this, right? And in fact, it happens that it's exactly the same, right? So as soon as you can detect, in fact, you can estimate with maximum likelihood, right? Easy problem. So you take the maximum likelihood. When you take the maximum likelihood, then, so you apply maximum likelihood. Now the problem is, so you the maximum likelihood in this case is very simple, because I assumed everything you take the log of the likelihood, or negative the log of the likelihood, because I want a minimum. And this is a very simple object. And you want to try to minimize it, right? Maximize the likelihood. So this becomes a computational problem. And there is what is very famously known as the computational gap. So in order for the maximum likelihood, so then it depends what algorithm you choose, right? So let me again do this picture. You have lambda IT here. Let's assume I normalize everything. You have 0 here. Lambda, let me put it to be 1. It's not 1, but let's normalize everything so it's 1. Then lambda, the threshold for maximum likelihood is here. And then the threshold at which different algorithms work depend on the algorithm. So what has been proved in the recent years is that essentially all the dumb, natural, reasonable algorithm stop working or begin working at the same place, right? And they are all, so whether you take gradient descent, Langevin, stochastic gradient descent, approximate message passing, all that works at the same threshold, which is n to the p minus 2 over, did I go? No, k, I'm sorry, k minus 2 over 2. So if you have a 3 tensor, this would be n to the 1/2. So this is a huge gap. In this region here, the maximum of the likelihood is a good is a decent estimator of your signal, of V, but you cannot find it, right? And then there is another threshold, which is here, at p minus 2 over 4. And there you have, this is the threshold for many other algorithms, which are not the natural gradient type algorithm. PK, yeah, sorry. So when k is 3, this is 1/4. When k is 2, when you have a matrix problem, then, of course, all these things are constants. K minus 2 is 0, right? But, so here, what are the algorithms that work down to here? First, there was the sums of squares that was done by Afonso Bandera and his collaborator. And then there were many others. There was the Kikuchi hierarchy. Then there was an algorithm which was kind of a bunch of gradient things collaborating, which was done by Giulio, Chiara Camarota, and Federico Ricci. And then there are many others. And in fact, this threshold was first, this one, was first introduced in the initial very seminal paper by Andrea Montanari and Richard in 2014. It was not a complete proof, but now there's a proof by Huang and myself, which is 2 months old, where you can do the stupidest algorithm, which is you take your tensor, let's say the 3 tensor, you unfold it as a long matrix, right? Of course, it becomes a very, very long matrix. And you compute the singular values of this very long matrix. So this very long matrix multiplied by its transpose. You look at the eigenvalues of that, and then you have what is called the BBP transition happening at a very sharp threshold there. So this is so all these algorithms stop there. I'm not saying that it's impossible to go below. Everybody trying, everybody stops at the same place. So if you have another method, try. If you beat this will be good. I don't know a good argument to say that you cannot beat it, in fact. But this threshold is the threshold for the local methods, gradient-like, right? Okay, so that's the story. And so now, if you apply the, now you try to apply this theorem. So you take your Tensor Pca problem, you take the stochastic gradient method, and you try to see what this does. So let me tell you, and so here, so normally this is done, all that happens on the sphere, because I assume that this thing was normalized. But here we did it on RD, because we wanted to have a unified presentation. So if you apply this theorem there, what do you find? So first, what would be the summary statistics? Right, so if you're in RD, if you're on the sphere first, this is the vector V you want to find. That's the sphere in high dimension. It's very easy to see that when you compute the population loss, that is just a function of the latitude. Right? The population loss is just a function, I forgot what it was, lambda m of x to the k or something like this. So, and m of x is just the x inner product with v. Right? So it's a function of this latitude. So you have a one-dimensional object when you're on the sphere. When you're on when you don't restrict to the sphere, you're on Rn, you have a two-dimensional object. Right? So you have it's natural to try this as a summary statistics. Good. And so what is the dynamical system you obtain? If you just obtain the trivial one. This thing, so what is the dynamical system? You will have the gradient of your loss. But this gradient will be, of course, 0 at the equator here, and you would have quite a bunch of derivatives that will be 0 here if k is large. Right? So your gradient flow it's not good to start from here. Right? So when you project in one dimension, what you see is just this. You have 0, 1, let's say if 1 is the altitude of this. Right? And you have a trivial, the gradient flow is just the gradient flow of this in the variable m. Right? So it's not very complicated. This is, of course, and now you may want to look at the stable point. This is definitely a stable point. Right? So is that a problem? Because, of course, you don't want to be there. You want to estimate. You want to be here. Your gradient descent would work. The result would be OK if you come close to 1, not if you stay at 0. But of course, the problem is that in high dimension, the mass of the equator here is enormous. The mass of the hemisphere is exponentially small in the dimension. Right? So every point is at the equator. Right? So if you start at random, you will start here. Right? So if you use this theorem first, then you will get convergence to this thing with just the gradient, the population loss, just this. Just the first term, f. But now if you say, if I start at random, then I want to understand what happens here. So I have to blow up what happens here. Yeah.
So in this case, to do online learning, you draw the WI
Yeah.
each time?
Yeah, one after the other. So if you blow up this by the right scale, which is 1 over root n here, if you blow up that, then you apply the theorem again, because you can, to this new summary statistics, the rescaled summary statistics. And now you get an equation like this where you do have a corrector and a diffusion. And then with these, you can compute how much time it takes to escape, which we know, in fact. And so I could write all these equations. They are in the papers. It's a pain in the neck. But you would see very easily that, where did I put it? Yeah. If you put so you can do it with a fixed lambda. So you could study, for instance, of course, there are other questions. You're not forced to start with random. You could start with warm start. You could start somewhere here. Right, which is, of course, very improbable. And then you would have the dynamical system that you expect. That would be OK. So, but if you start at random, you have to rescale. You reapply the same theorem, but now you have more terms. And these more terms will tell you how much time it takes to escape this mediocrity and get to the signal. OK, and let me tell you, it's a long story. You find what you should find. And in particular, if you put your lambda, your signal-to-noise ratio in the right scale, you find in this scale, then you find a critical value. So let me say why. If you put yourself in this scale, what you will find here in the end is an Einstein-Uhlenbeck process. That is, which would transition from being stable to unstable. So you know what this Einstein-Uhlenbeck is, right? It's whatever. I'm sure you know better than me. So, but when it's stable, of course, it's bad news. Because stable means you cannot escape 0. When it's unstable, you zoom away, right? So that's the transition, very natural. All right? So this just confirms what we understand for a simple model. All right? So if you want to now go to, and all that is, of course, done in detail. So let me give you a little less trivial example. Okay, let me just say there are still some surprises. For instance, there are some spurious, unstable things which I have never seen before. So with this approach, for the Tensor Pca, there are possibility of getting stuck even with a warm start, right? Which seems a little strange. And of course, this disappears when your lambda tends to infinity. Okay, so there, even with a more warm start, if you're not warm enough, you can get stuck in something which is not the optimal solution. Right? That's just for the expert. All right, so now. Yeah. No, you're stuck at something which is, you start warm, you become a little warmer, but not warm enough. Okay, so now let me give you examples a little less trivial. So I will start with a two-layer network for classification. This is a ridiculous example in some sense because, of course, for this classification, nobody would take a two-layer network. We would take a one, but just to try our new concepts. Okay, so I take a binary Gaussian mixture. And so let's say, so my data has this form. It's YL, XL. This is the class, only two classes. So this is Bernoulli. And I take the interesting case where it's 1/2. So you have the two classes are the same size. And the XLs are IID, Gaussian, with a known, so it's binary mixture and you know the covariance. Okay, so what does that mean? When y is 1, the mean of XL is mu. So mu is here. When y is, so this is y equal to 1, if I'm not mistaken. And when y is 0, it's negative mu. So you have a Gaussian bump around this one, a Gaussian bump around that one. That's the distribution. Okay, and of course, depending on lambda, these two bumps can be very separated or can merge. Right? Good. So that's your data. And you want to classify, so you have this data, you want to classify by, so let's say mu is of norm 1. You want to classify with two layers in the simple thing. So you have here capital N thing. So you have a first vector W1 that goes to 1 here, right? The linear, these are the links. You have another one that goes to 2. So you have W1, W2. And you do classification here, let's say with, here you put the ReLU. Then you have two numbers, V1 and V2. And here you do sigmoid. That's your neural net, right? You just play. Okay? So you understand what I mean with this picture? I don't know, big silence, people saying, what do they think? Of course we know. Okay, good. So, so this creates, and then of course I have to give you the cost. So the cost, you take a binary cross entropy. With some L2 penalization. I'm sure you also know what that is. Okay? If you want me to write the formula for L, I can. Needed or not? Okay, not needed. So now with that, I've defined an architecture, a loss function. I have my function capital L, right? And I can do now, I can try to apply my theorem. Right, I have a sample. What happens? Of course, I have to tell you, everything depends on where you start. But first I have to find what is a natural summary statistics. So the summary statistics in this case is of, the one we found is in dimension 7. So suddenly, instead of being, a very simple dynamical system as before, dimension 7 can become a little harder to see. So the summary statistics we pick is where, so is it 7, 1, 2, 3, 4, 7, yeah. So where the mi's are the wi inner product with mu, so let me put a dot because you don't like the brackets, and the rij are where this wi orthogonal is w minus mi mu. Okay? So you see a priori this, so this is the, these are the 7, I'm telling you, this is a summary statistic. It works, my condition works. And now, of course, I have to tell you the step size, because I needed this localizable, delta n localizable thing. So I'm telling you that if you take delta n to be a constant over n, the system is delta n localizable. Oh, by the way, who is little n? Essentially, my dimension here is, it's like capital N, it's 2n plus 2, right? Because here you have, each vector is dimension n, you have 2 of them. That's 2n, and here you have 1 and 1, right? So if you take C over n, this is localizable. The theorem works, all right? So if you take little o of C, little o of over n, right? So if you take this, it works too. So if you take this regime, but then in this regime, you have G equals sigma equals 0. For these delta n, the limit you get is the one that you would get in finite dimension, right? The flow, the gradient flow. But for the critical thing, it becomes more fun. So for the critical thing, for this one, sigma is 0, but you have a corrector. G is non-zero. So the effective dynamics are not the population flow dynamics. And they are much better, in some sense, to escape, again, as we described before, to do interesting things. So let me describe what the phase diagram is for this thing. And you will trust me. So a priori, we're in dimension 7. But so drawing a picture in dimension 7 is complicated. But for all the fixed points of my, so again, I have this limiting system with no sigma, and this will be my field, if you want, minus f plus g. For this, all the fixed points of that have rij equals 0, and they have always mi equals vi. It's just compute, and that's what you find. So in the end, this reduces what you're looking at from dimension 7. All these disappear. All these are equal to that. So finally, you can write a phase diagram in dimension 2, right? So in dimension 2, here's the phase diagram. So if you choose, so I didn't write what this was. Alpha here is the strength of my L2 regularization, right? So when alpha is smaller than 1/4 with the normalization we have, here's what you find. Here you have an unstable fixed point. Here you have a quarter circle of fixed points. Here too. These are unstable. And here you have a stable fixed point, and here too. Interesting. Okay, not too complicated, but already you scratch your head, at least we did. So once you have this, you can say, okay, so if you run your thing, you start at random, blah, blah. So you can try to compute the probability that you end up in one of these, which are in fact the optimal classifiers, or in one of those, right? Because your dynamical system will tend to, in finite but long time, to end up there. So in fact, the probability to end in a bad thing is 1/2. The probability to end in a good thing is 1/2. But you can't distinguish this. You run your thing, in half of the cases it would have done a good classification, in half of the cases it would be in one of those terrible places. All right? Now, the story is not finished. All right, it went there. But of course, it doesn't really, your dynamical system will not really touch. It will come close in finite time. Right? You don't hit the stable manifold. So what do you want to do then? You want to zoom. Right? So you take this now and you take your system, your summary statistics, near a fixed point, unstable, and you zoom, right, to see what's going on. When you zoom, so here we already had a system where we had a G. We had the corrector term. But now when you do that, you have not only a G, you have a diffusion term. So when you zoom now in the proper scale, it's also a 1 over root n, you get a diffusion term. And now, same question than we had before. Will this diffusion term be good or not? If the diffusion term is unstable, right, if it creates like an Ornstein-Uhlenbeck, which pushes you away from there, that's nice. Because then you come close to this bad thing, but if you wait longer, then you are repelled, and you may have a hope to end up there, right? So of course there is a transition, all right? And you can do all that completely. All right. So given the time, when did we start? An hour? 1
hour ago.
So you decide, do you want to see something about Xor, which is much more fun? Okay, so why did we do that? This is crazy again, as I said. If you want to classify something like this, you don't need 2 layers. We did this 2-layer thing because when we tried to do the Xor thing, we saw something crazy, and we said, okay, let's do that as something a little simpler where we can understand things faster. So, but already this picture is, and there's much more to say. These points are super interesting. It's a zoo with of all sorts of animals which you can pet for a long time. So now, so all that is to tell you that, so of course this is valid for the critical thing, this new regime, right? Critical delta, which is C over n. If you looked at C, at a delta which is much smaller, you wouldn't see any of this, right? It would be just the gradient flow. Okay, so let's take the Xor problem. So I will take a simple Xor thing. So I have, again, my data are again YL, XL as before. So this is again Bernoulli, right? 1/2, 0, 1. And XLs now are an Xor type thing, which is half of Gaussian centered at mu, is variance I over lambda plus and that is if y is 1 in the first class, and in the second class it's the same thing with a different mean. For the moment we don't complicate things, we fix the covariance. So you see where you have 2 vectors, let's say orthogonal, right? You may have mu here and negative mu here. So you have a bump here, a Gaussian bump there, and then you have a nu here and negative nu here, and you have that. So your 2 classes are either this or that, like an Xor table, okay? And you do the same classification. You take your architecture is again sigmoid of, so you have a first layer, exactly the same structure. The structure I wrote, you just do the same. 2 vectors, you have the W's, then you apply a ReLU, and then you take a sigmoid. So, and we took something simple. We assumed the first dimension where things are interesting, where this W was K by D, right? And when K was 4, the simplest thing, because otherwise it becomes a big space. So I won't write everything, but here we found the summary statistics was in dimension 22. which you can describe. You know, I've described a 7-dimensional U in the former problem for you. You had the V's, the M's, or this R, whatever. So you have something of the same nature, more complicated, which is 22-dimensional now. So go think in dimension 22. Now, interestingly, what you find is that so again, you get a limit theorem where you can get exactly the two phases I was giving before. A ballistic phase with a corrector term, as we had before. And then if you zoom on the critical point, you can get a diffusive phase. But what is this? Okay, now I cannot do this nice picture I was doing there. So over there I had how many connected components? I had 1, 2, 3, 4, 5, right? I had these 2 arcs and 3 points. Here I have, as I said, 5 to the 4, which is 625 connected components of the fixed points. When you look at your dynamical system, there are 625 places where your dynamical system can end up, right? So suddenly it's a little scary. And then out of these, you have factorial 4, which is 24. So believe me, we computed 24 stable ones. So remember the picture I just drew? You had these unstables, and you had these stables, and this one was unstable too. And you wanted to be here, but you could end up there with positive probability. So here you ask yourself, what is the probability to end up in a good one? So of course, what does probability mean here? Of course, you could also do warm start, right? Remember, let's go to back to Tensor Pca. You had one bad thing, which was 0. You could start from there. If you start at random, so let's go back to Tensor Pca. If you start at random, in fact, you start from the stable critical, from 0, which was stable but bad, right? And if you had a warm start, then you could start away, and then you go to 1. Here, so of course you could also have warm starts, but guessing a warm start when you have 600 in dimension 22, when you have 625 bits, a little more complicated, right? But so what is the probability to end up at a stable 1? You can compute. It's 3 out of 32. Nobody cares. I don't care about 3 out of 32. But the important thing is that it's positive, right? It's not going to 0 with something, right? So at least a fraction of what you do is not stupid, right? Which is good, because then, of course, if you do that, maybe you can just do testing. You do training, and then you take what you've done. Some of them will, a finite fraction of it, because this probability is positive, will be reasonable, right? And you can, and then just keep that, right? This is like 1/10. So 9/10 of what you do will be useless. 1/10 will be reasonable. Okay? So I will stop there. I will not give you more about those critical points because it's a bit of a pain. Yeah. So I will stop here. I'm sorry?
Does your theorem say anything about stochastic, not stochastic, gradient descent?
Yes, because of that gradient descent is this term.
No, but if you apply gradient descent in high dimension,
Yeah.
for instance, on the problem of the tensor problem, you fail at the same point. But there are cases where stochastic gradient descent doesn't fail, where gradient descent would fail because you don't have maybe the stochastic term or something like that.
Yes, this is,
So that in some cases you don't have the stochastic term.
So what okay, there are two ways to answer your question. First is, I could think of what you're saying being, what if you do gradient descent for the empirical flow, right? Which, so that would be like stochastic gradient descent with full batch, okay? So this is a different, so that Okay, that's a different question. The other question is, what if you do gradient descent for the population loss, not the empirical one? If you do gradient descent for the population loss, which of course you cannot do because you don't have the population loss in your hand, but if you were God and you could, then you would get this term for the projection. And so we're already saying that these terms play a big role. In fact, they are the one that explain, for instance, you know, when you start from, like in Tensor Pca, you start from 0, it's hard to escape, and these terms do that. In the other examples that we have here, where we don't even have sigma. You have sigma typically, as I said, once you become close to a stable manifold and you want to escape. But even in the ballistic phase, where you start from somewhere and you're just moving, you have the corrector term. And this corrector term plays a very big role. And I believe it is really related to the fact that it's SGD and not GD, and not gradient flow. You wouldn't have that. So people keep saying that, in fact, and I wondered why. So it's true that for Tensor Pca, it doesn't play a role, because the difficulty is too hard in some sense to escape. But many people say SGD, you know, if you ask Yann, Lequin, Léon Bout, whatever, they will tell you SGD is much better because it's irreversible. It's not like Langevin, which is reversible dynamics, or gradient flow, which is a limit of reversible, right? Yeah. So it is, yeah. So this is, I believe, so this G is typically an irreversible term. It's not a gradient term. So it plays a role. So this is the first evidence that I see of the role of irreversibility of this flow. Okay? And when I was just preparing these talks, I received, you know, from this thing which online send you papers you're supposed to be interested in. And one of them was somebody, I hope he or she is not in the room, but because I will sound ignorant here, which was doing dynamics for p-spin, going faster than we all know, the trap model for, I mean, p-spin can be very slow, but going faster by adding some irreversible component, right? So it's not this, but it's the same idea. So it's a natural idea which has been around, and so my answer is yes, this G is an irreversible term, this corrector term. So, yeah.
Maybe you say it, but for the Xor case, what is the number of hidden layers of neurons you use? Is still 2 or?
For which one? For the Xor? Yeah, 2. It's the same thing, 2. Yeah.
And you have some cases where the input dimension would be fixed, but others the hidden dimension will grow to infinity. And then what would be your insight about the type of statistics?
No, that is a fantastic question, but you know, it will come. This paper is not finished. If you want to do it, please be my guest. This is because you know when you get 22 dimensions.
Because the infinite dimensional problem, it has to live to measure space of measures.
Yeah. You're right. Yeah.
When you see the vector space, but
Yeah.
it's not the same problem.
Yeah. So yeah. Here we, you know, when we started that was supposed to be a stupid example, which would last 5 minutes, and then when you get 625, then you stop, you write the paper, and you say, let's breathe and go to something a little less. But you're right. Of course, the important thing would be to have larger layer. There is supposed to have a transition between, you know, the regime where it's very large and this type. There is a very nice recent paper by Florent and Lenka, Florent, Chakala, Lenka, Zdeborova, and younger people who I hope are not here because I forgot. So this where they look exactly, try to understand this transition between the mean field regime that was done by I don't know, Andrea Montanari, Eric van den Eyde, and all this group, and the other regime, and with stochastic gradient descent, and they have some kind of understanding of that.
Other questions? So maybe just, I mean, it's a question and comment. So I think it's, you didn't say, but maybe it's in the paper, it's the all you have done also apply to physicists a long time ago, to the teacher-student neural network, in which indeed the online learning at the end is an equation on the overlap, matrix overlap of all the nodes, which are exactly, I think, your...
My summary statistic.
Exactly. So I think it's, in that case, you can make it rigorous, all these full studies.
In fact, we got in that through this thing. There was we started with Reza, as you know, with Reza and Okosh with spin glass, then Tensor Pca, by doing a long hierarchy of equations and all sorts of mess. But then we had another paper where we looked at rank 1 things, which included, of course, the rank 1 included the Tensor Pca, but also all these teacher-student things, perceptron-like things. But then, so it was of the same spirit. We introduced what we call this information exponent there, which was 1, 2, larger than 3. But there, in some sense, there were all these, so there are plenty of models like that, which are statistical, but where the natural summary statistics is 1, in dimension 1, or maybe 2 if you don't restrict on the sphere, right? So, because then you would have the radius and the overlap. And so for all these models, yes, you're right. We would get something that we could have included that here. But then we began thinking, what happens if it's not rank 1? Because what was this information exponent we had introduced was because a classification of dynamical system in dimension 1, even babies can do that, and we could, because we are not expert in dynamical systems. So, but then we said, what happens if we do a dynamical system which is in dimension 22? And then boom. So but interestingly, again, let me repeat the important thing. If you do it at a subcritical scaling, then you don't see any of that. You see something much simpler. You see the natural gradient flow, right? It's just that there is this critical regime where things happen. So if your system is reasonable, you don't want to go to the critical regime. But you go to the critical regime because this is the one that would tell you, if you follow something and you get kind of stuck, like in Tensor Pca, then if you go to the critical regime, then it tells you how you escape, right? And by the way, in this example, the diffusion 22 whatever, the diffusion matrix is dimension 1. So it's really very degenerate, right? So it's a hypoelliptic operator, if you want. So it's not at all the usual elliptic. When you have a dynamical system perturbed by noise, noise is not going in all directions. The way you escape things is a little more complicated. Okay, so there is room. I mean, this thing is open. And in particular, a natural question would be to understand the meta question of understanding how do you find summary statistics. Right here, what do? We take a model, another model. You look at them, you compute, and you see. But because the population loss is a function of a few variables. But if you don't have that, maybe you can have approximate summary statistics, like in the Papian-Donoho, Han-Donoho thing. When you get this BBP transition, you see a few modes coming out. These are the important variables in this neural collapse phase. Maybe you could do something of that nature there. Maybe, in those examples, they are done by hand. Maybe in more serious things, you have summary statistics, but the meta question of knowing if they exist, what they are, probably you have to solve a crazy PDE somewhere. This is completely open. This is only the very, very beginning of something.